Right now, as you watch this, your electricity bill is paying the price for a problem that has a completely free or almost free solution hiding in plain sight on your windows. On hot days, up to 87% of heat gain in our homes enters through our windows. Not through the roof, not through the walls, but through those clear panes of glass we trusted to bring in light and keep out the elements. What if you could flip that around entirely? What if you could keep the light, keep the view, and block the heat at the same time? And what if the science behind doing that was already proven, documented, published in journals, and available for you to use starting today? There are 7 different window hacks in this video, and they range from something you can do in the next 10 minutes with materials costing less than the price of a meal, all the way to a revolutionary new transparent material, just confirmed in a published scientific study in December 2025, that could eventually make your windows perform better at blocking heat than your own walls. Stay until the end of this video because the last 2 hacks are the ones that almost nobody knows about yet. And one of them involves a material currently only available in a physics laboratory at the University of Colorado Boulder that blocks heat transfer at levels that would have been considered impossible just a few years ago. But before we get there, we need to understand a little bit of physics. Then every single hack in this list will make perfect sense. Sunlight contains 3 types of energy: visible light, which is what we see; infrared radiation, which is what we feel as heat; and ultraviolet rays, which are what causes sunburn and fading. Regular glass lets all 3 pass right through, and that is the root of the entire problem we are dealing with every summer. A thin sheet of silica that was designed centuries ago for one purpose only: to let light pass, with absolutely no consideration given to the invisible heat freight that comes along with it. Infrared light is the real troublemaker, accounting for 50% of solar energy. You cannot see it, but you definitely feel it as heat. And this invisible energy passes right through your glass and warms up your furniture, floors, and walls. Air conditioning turns out to be expensive, especially right now in 2026, when fuel costs have risen sharply across the United States due to ongoing supply disruptions due to the Middle East conflict escalation. While regular glass is essentially useless at filtering heat, the science of making glass and window surfaces selectively block heat while transmitting light has advanced enormously, and the solutions now exist across a wide spectrum. From inexpensive films, you apply yourself to engineered coatings that went through peer-reviewed physics research. And you need to know each and every single one of them. Let us begin with hack number 1, the one that you can implement this week, and one that is backed by decades of energy research: solar control window film. Modern heat control window film uses spectrally selective technology with microscopic layers thinner than human hair, and these nanotechnology coatings can reject up to 97% of infrared radiation while still allowing 70% or more of visible light to pass through. Think about that for a moment. A thin, transparent sheet that you stick directly onto your glass, and it almost completely intercepts the invisible heat energy while allowing normal daylight to flood your room as if nothing were there at all. These films are made from thin layers of polyester or vinyl and often use metallized coatings or advanced optical layers to improve their heat-blocking performance. And the critical thing to understand here is how they actually do this, because it is not magic, it is physics. The infrared portion of the solar spectrum is reflected by the coating back outside the building. This invisible reflected solar infrared radiation returns to the outside and is thereby prevented from entering the cool interior of the building. And the result is a major reduction of the solar heat gain through the window without significant loss of visible light transmitted through the glass. Studies and real-world data show that homes with reflective window films can lower cooling costs by up to 30%, and that is not a theoretical laboratory finding. That is a number drawn from real buildings and real climates over extended measurement periods. Now, the way that professionals and engineers measure how much heat a window allows through is with a number called the Solar Heat Gain Coefficient, or SHGC. And this single number is one of the most important pieces of data you will ever look at when evaluating anything related to window heat management. The SHGC is expressed as a number between 0 and 1, with a lower number indicating less solar heat gain and a higher number indicating more solar heat gain. And, for example, a window with an SHGC of a 0.25 will transmit 25% of the solar radiation that strikes it while reflecting or absorbing the remaining 75%. Clear glass has an SHGC of 0.84, meaning it allows an 84% of the solar radiation that hits it, which is why a room with untreated glass windows on a summer afternoon can feel like a greenhouse even with the air conditioner running at full power. You do not need full window replacement to change the SHGC. The right window film can significantly reduce solar heat gain without touching the frame or glass unit. This matters because it is a faster and more affordable upgrade, and films can deliver strong heat reduction at a fraction of the cost of new glazing. When you go shopping for window film, the most important thing to check on the label is that the visible transmittance value is higher than the SHGC value, because that means the film is letting through more light than heat, which is exactly what you want. Window films are generally a retrofit option, intended to fix a problem with excessive solar heat gain and solar glare from an existing window, while window coatings are generally applied in a glass factory, usually in a large vacuum chamber. And this distinction matters because one you can do yourself this weekend, and the other requires a completely new window installation. For the do-it-yourself application of window film, the process involves first cleaning your glass absolutely spotlessly, because even microscopic dust or oil contamination between the film and the glass surface will cause bubbles and adhesion failures over time. Most manufacturers offer 10 to 15-year warranties on professionally installed films, covering both materials and workmanship, and DIY installations typically void these warranties entirely, leaving you without protection if something goes wrong. And given that quality films should last 10 to 20 years, this warranty coverage is crucial protection for your investment. So hack number 1, the Solar Control, or spectrally selective window film, is affordable, available at most home improvement stores, takes a few hours to apply per window, and gives you a scientifically verified reduction in infrared heat entering your space while preserving your view and your daylight. But while that one handles the heat that tries to come in through the glass itself, there's a completely separate problem happening at the edges of your window, and that is where hack number 2 quietly delivers results that most people completely overlook. Tiny gaps around windows let hot air seep in and cool air escape, making your AC work harder, and using weather stripping or caulking creates an airtight seal, enhancing insulation. This sounds absurdly simple, and it is, but it is also one of the highest return energy improvements you can make to a home, because all the best window film in the world means nothing if hot air is freely flowing around the frame of the window, bypassing the glass entirely and pouring directly into your living space. The way to tackle this is with a combination of flexible foam weather stripping tape applied to the window sash and frame, and exterior-grade silicone caulk applied to any visible cracks or separations between the window frame and the wall surrounding it. And both of these products cost almost nothing and can be applied in an afternoon. Now here is where the story gets significantly more interesting, because while films and sealing address the 2 most immediate entry points for summer heat, the next hack on our list operates on a completely different physical principle, and it involves geometry, specifically the geometry of the honeycomb. Cellular shades, often referred to interchangeably as honeycomb shades or insulating window coverings, get their name from their unique construction, and cross-sections reveal a honeycomb-shaped pattern that forms a network of air pockets, trapping air at the window. This design is the secret to their powerful insulation properties, making them stand out from more traditional blinds or curtains, and these pockets of air act as a barrier, helping reduce thermal transfer and keeping interiors cozier in winter and cooler in summer. Air happens to be a fantastic insulator, and a 3/4 inch pocket of air has an R value of 0.87, and the honeycomb cellular shade exploits this fact with a repeating geometric structure that multiplies this effect across the entire surface of your window. Cellular window shades are designed with R value in mind, and the honeycomb-shaped fabric uses air pockets to slow the movement of thermal energy, and the result is something that feels like hanging a section of insulated wall in front of your window, except it can be raised in a second when you want your view back. In heating seasons, tightly installed cellular shades can reduce heat loss through windows by 40% or more, which equates to about 10% heating energy savings. And in cooling seasons, cellular shades can reduce unwanted solar heat through windows by up to 60%, reducing the total solar gain to 20% when installed with a tight fit. Single-cell honeycomb blinds achieve R values around 2 to 3, while double-cell versions reach 4 to 5, and for context, standard windows rate R1 to R3 depending on glazing, which means adding quality cellular blinds can effectively double your window's insulation. While the single-cell option is good for moderate climates and smaller windows, for larger windows and colder climates, double-cell options provide better insulation and energy efficiency. And the triple-cell version, which contains 3 full rows of air pockets stacked against each other, is the maximum performance option available for extreme heat conditions. Cellular shades that operate on side tracks are most effective at increasing the R value of windows, and those that open from both the top and bottom allow users to most effectively control daylight entering the home. Now, while cellular shades give you the highest R value of any window covering currently on the market, they do block the view when they are closed, which is fine for certain rooms and times of day, but not ideal for a living room or kitchen, where you want both cool temperatures and unobstructed views simultaneously. This selective filtering is exactly why thermal films crush traditional blinds and curtains, because those old school solutions block everything: heat, light, and your beautiful view. That tension between insulation and visibility has been one of the central engineering challenges in window technology for decades, and it brings us directly to hack number 4, which is where the science becomes genuinely fascinating, because it involves a coating technology that was first commercialized in the 1980s and has been continuously improving ever since. Low emissivity glass, almost universally called low E glass, is a product that applies an ultra-thin transparent coating of metallic oxide directly onto the glass surface during the manufacturing process inside a large vacuum chamber. And this coating works by a mechanism that is slightly different from solar film. The so-called low E coatings offered even greater insulation of a building's interior spaces from cold outside air temperatures. These coatings are applied to one of the interior glass surfaces and work by reducing the emission of long wavelength infrared radiation from the warmer interior pane of glass, or by reflecting that radiation from the outer pane back to the inner pane, and the result was a reduction of heat loss from the warm interior to the cold exterior on cold winter nights. But here is where it becomes really clever, because in hot climates, the same principle is engineered in the opposite direction, and this second generation of low E technology is sometimes called hot climate low E. The generic name for the new technology is low solar gain low E coating, but it can also be called hot climate low E coatings. And these new coatings work by extending the spectral selectivity characteristic of a conventional high solar gain low E coating, bringing it from outside the solar spectrum to the edge of the visible portion of that spectrum. Low E coated windows are designed with a thin, transparent layer of metal oxide applied to the glass, and this coating reflects infrared heat while letting visible light pass through, making it an effective solution for controlling seasonal solar heat gain. These windows typically have solar heat gain coefficient values between 0.25 and 0.35, which is a significant improvement compared to clear glass, which can reach an SHGC of 0.70. Research shows that upgrading to low E coated windows can cut annual cooling energy use by up to 30% in hot climates and lower heating costs by 10 to 20% in colder regions. And if you do not want to replace your entire window, there is a retrofit version of low E technology in the form of low E window film, which brings this same metallic coating benefit to your existing glass. 3M Company introduced insulating low E window films in the early 1970s as a solution to transform standard glass into low E glass. And decades of refinement have made these products significantly more effective and easier to work with than the original versions. During the cooling season, window film increases the amount of the sun's incident energy that is reflected and absorbed by the glass, thereby reducing what is transmitted into the building. And during the heating season, window film increases the amount of man-made heat from the HVAC system that is reflected back inside the glass, thereby reducing what is lost to the outside. Low E films work particularly well in older homes with original windows. They can reduce heat loss by 30 to 50%, making rooms more comfortable and cutting heating costs. And the summer cooling benefits are substantial too, typically blocking 40 to 60% of solar heat gain. Now, while low E glass and film operate as a passive fixed coating that always does the same thing regardless of conditions outside, the next generation of window technology moves beyond passive and into something far more sophisticated, something that actually responds and adapts to what is happening outside your window in real time. This is hack number 5, and it is called thermochromic or smart glass. And while versions of it are not yet in every home, the research behind it is rock solid, verified across multiple international laboratories. And commercial versions are increasingly appearing in new construction projects worldwide. Architectural thermo-responsive dynamic windows offer an autonomous solution for solar heat regulation, thereby reducing building energy consumption. And the key word there is autonomous, meaning the window makes its own decision about how much heat to let through based on temperature, with no human intervention needed. The most widely researched material for this application is vanadium dioxide, a metal compound that undergoes a remarkable phase transition at a specific temperature, shifting from a transparent state that allows infrared light through to a reflective state that blocks infrared while still transmitting visible light. Tungsten-doped vanadium dioxide allows fabrications of windows that might be cooler in the summer and warmer in the winter, and the fact that this switch happens automatically in response to temperature without any electrical power, without any wiring, without any smart home system, makes it a genuinely elegant engineering solution. Through a global scale analysis, researchers explored over 100 material samples and executed more than 2.8 million simulations across over 2,000 global locations. And World Heat Map results revealed that thermo-responsive windows are especially useful in climates where buildings demand both heating and cooling energy. And beyond the thermally activated version, researchers at North Carolina State University have gone further, developing a version of smart glass that responds not to temperature, but to an electrical signal, giving the user direct control over exactly which wavelengths of light and heat are blocked at any given moment. Researchers have now shown that you can effectively tune the wavelengths of light that are blocked when you inject lithium ions and electrons into a related material called tungsten oxide hydrate. And when lithium ions and electrons are injected into the hydrate material, it first transitions into a heat-blocking phase, allowing visible wavelengths of light to pass through but blocking infrared light. And if more lithium ions and electrons are injected, the material then transitions into a dark phase blocking both visible and infrared wavelengths of light. What this means in practical terms is a single window that can be in any of three states: fully transparent and heat emitting on a winter morning when you want warmth, heat blocking but still clear on a summer afternoon when you want light but not heat, and fully darkened when you want privacy or complete light control. Our work demonstrates that there are more options available, and specifically, we have shown that you can allow light to pass through the windows while still helping to keep buildings cooler and thus more energy efficient. And this kind of precision control over the relationship between light and heat at the glass surface represents a fundamental shift in what a window is even capable of doing. Now, while the electrochromic and thermochromic smart glass solutions described above are progressively appearing in commercial construction, there is one more near-term technology that combines quantum physics and machine learning in a way that feels almost science fictional but is absolutely real. And this one was published at the University of Notre Dame in April 2024 in the journal Cell Reports Physical Science. Assisted by quantum physics and machine learning, researchers developed a transparent window coating that lets in visible light but blocks heat-producing ultraviolet and infrared. And the coating not only reduces room temperature, but also the energy consumption related to cooling, regardless of where the sun is in the sky. That last part is critically important because almost every window coating loses some of its effectiveness as the sun changes angle across the sky throughout the day. When the sun is low on the horizon in the morning or evening, light hits the glass at a steep angle, and many coatings perform poorly at those angles. Their model produced a coating that both maintained transparency and reduced temperature by 5.4 to 7.2 degrees Celsius in a model room, even when light was transmitted in a broad range of angles. 5 to 7 degrees Celsius may sound modest until you realize that is the difference between a room that feels comfortable and one where you immediately reach for the air conditioning remote. And achieving that reduction purely passively through a transparent coating means zero electricity, zero moving parts, and zero ongoing cost. Now we arrive at hack number 7, the one that is at the cutting edge of published physics research as of the end of 2025, the one that almost nobody knows about yet, and the one that could change the entire architecture of building windows within the next generation of construction. It is called Mochi, which stands for Mesoporous Optically Clear Heat Insulator, and it was developed by a team of physicists at the University of Colorado Boulder, led by Professor Ivan Smalyuk, with the research published on December 11, 2025 in the prestigious journal Science. The team's material, called Mesoporous Optically Clear Heat Insulator, or Mochi, comes in large slabs or thin sheets that can be applied to the inside of any window, and it works a bit like a high-tech version of bubble wrap. Mochi consists of a network of hollow silicone nanotubes arranged in a highly uniform pattern, and air makes up more than 90% of its volume. Yet the solid framework keeps those air pockets stable and evenly spaced. Now, to understand why this is so remarkable, you need to understand the previous best attempt at transparent insulation, which was aerogel, a material that has been used in industries from construction to space exploration, and which NASA has deployed inside its Mars rovers to keep sensitive electronics warm in temperatures that drop to minus 90 degrees Celsius. Aerogels also rely on air-filled pores, but those pores are typically arranged in a random pattern that scatters light. This is why aerogels often appear cloudy and are sometimes referred to as frozen smoke. And the CU Boulder team wanted an insulating material that would maintain clarity while providing strong thermal resistance. The engineering challenge here is profound because the same structural feature that makes a material insulating, which is tiny pockets of trapped air, tends to scatter light and make the material opaque or hazy. And nobody had previously managed to solve both problems simultaneously at a useful scale. Many insulating materials rely on trapping air, but if the internal pores vary too much in size, they scatter light and allow heat to pass. And to work well, an ideal window insulator needs pores smaller than visible light and smaller than the distance air molecules travel before colliding. And at room conditions, that distance is about 60 nanometers. In normal aerogels, heat passes through the air or gas trapped in the bubbles in a process much like a miniature game of pool, where heat energizes atoms in the gas, which then bang into other atoms, transferring the heat energy. However, the bubbles in Mochi material are so small that the atoms inside cannot bang into each other, which prevents heat from being transferred through the material. Researchers at the University of Colorado Boulder created a coating just 5 millimeters thick that contains millions of tiny air bubbles, and it allows 99% of the available light to pass through while reducing heat transfer by 90%. Read that again slowly. 99% of visible light passes through, while 90% of heat transfer is blocked. Consider that tests showed that thin Mochi sheets transmit more than 99% of visible light with almost no haze, while ordinary window glass typically transmits less than 92%. meaning this insulating material is actually more transparent than the plain glass it is designed to replace. The team demonstrated thermal conductivity lower than that of still air, as well as an average light transmission above 99%. And Mochi glass units can provide a similar rate of heat transfer to high-performing building roofs and walls with thicknesses comparable to double-pane windows. That last sentence is extraordinary. A window that insulates as well as a roof or a wall while remaining clearer than ordinary glass. According to the team's calculations, a building retrofitted with Mochi windows could boost its energy efficiency from around 6%, a typical value in current buildings, to over 30%, while reducing the heat energy passing through by around 50%. Although Mochi is not yet commercially available, its CU Boulder developers said the ingredients used to make their transparent insulator are common and inexpensive. And they also noted that its current complex manufacturing process could also be significantly optimized, raising the possibility that transparent insulators could be available sooner rather than later. The researchers say Mochi is long-lasting, up to 20 years, and almost completely transparent. And the team has already demonstrated that they can manufacture square meter-sized slabs of the material through a process they believe is scalable to industrial production. As polysiloxane is already widely used to seal the edges of commercial windows, one straightforward application could be to insert Mochi between the panes of standard double glazing for better insulation, which means this material is not a replacement for the entire window system, but rather an insert that works within the infrastructure that already exists in billions of buildings worldwide. Now, let us take a step back and look at all 7 of these hacks together, because the real power comes from understanding how they stack, layer, and complement each other, each one addressing a different physical pathway by which heat enters your space. The weather stripping and caulking seal the gaps so that conditioned air cannot escape and hot outside air cannot infiltrate around the frame. This is the foundation, the base layer, and without it, everything else is compromised. The solar control film sits on the glass itself and acts as the first line of defense against the infrared portion of solar radiation, intercepting the heat, carrying wavelengths before they ever touch the interior surface of the glass. The low-E coating, whether as a film retrofit or as a factory-applied coating on new windows, adds the additional dimension of managing long-wave infrared radiation, the radiated heat that passes from one surface to another even without any physical contact or air movement. The cellular honeycomb shades create a buffer zone of trapped still air between the glass and the living space, exploiting the fact that stationary air is one of the most effective insulating materials known, and they do this through one of the most elegant geometric designs found anywhere in nature. The thermochromic vanadium dioxide smart glass responds passively to temperature, making its own decision about when to block solar heat gain without requiring any human input or electrical infrastructure, making it the solution for buildings that need to be set and forgotten. The electrochromic tunable glass from the North Carolina State Research goes one step further and puts the user in direct control of precisely which wavelengths are admitted or blocked at any moment, creating a window that can be customized to the exact needs of any given hour, season, or climate condition. And then, above all of this, still only in the laboratory but confirmed by peer-reviewed science and with a clear path toward commercialization, Mochi waits in the wings as the material that may eventually make the walls and windows of a building thermally equivalent for the first time in the history of architecture. In practice, customers often choose a window film product not only to save energy or cost, but also to mitigate issues around glare, excessive light, daytime privacy, or inconsistent appearance of the building. And this reality means that the selection of the right hack is not purely a physics exercise, but also a personal one that depends on your priorities, your budget, and the specific orientation and size of your windows. A south-facing large glass wall in a hot climate calls for a very different combination of these solutions than a north-facing bedroom window in a temperate zone. And getting that matching right is what separates a meaningful reduction in your energy bill from a marginal one. Significantly reducing the solar heat gain coefficient that can block unfavorable heat during the summer can actually harm blocking favorable heat during the winter. And this is the nuance that many online guides skip over entirely, because the goal is not simply to block as much solar energy as possible in all directions at all times, but to block heat in summer and retain it in winter, which is precisely what the combination of spectrally selective films, low-E coatings, and smart glass technologies are designed to do. You can balance for all seasons by selecting films that limit summer heat, yet still allow useful winter sun, especially on south-facing windows. And that kind of year-round optimization is what transforms a window from a liability into a genuinely contributing component of your home's thermal envelope. The economic argument for acting on this today is more compelling than it has ever been, because the cost of doing nothing is rising faster than the cost of any of these solutions, and the payback period on something as simple as quality window film is measured in months, not years, at current electricity prices. Scientific research on energy savings shows that window films can reduce building energy consumption by 10 to 15% in hot climates, making them one of the most cost-effective upgrades you can make. And in a world where electricity prices are rising and supply is increasingly uncertain, that percentage represents real financial resilience that you can build into your home this weekend. The broader picture here is one of a technology ecosystem that is maturing rapidly, where the gap between laboratory discovery and consumer application is shrinking, where materials like Mochi that are currently being studied under microscopes in university physics labs will eventually arrive at hardware stores, and where the combination of existing proven solutions and emerging science is giving homeowners more control over their own thermal environment than any previous generation has had. While windows cover about 8% of most structures, they can contribute nearly 50% of total heat exchange. And as modern architecture shifts toward larger glass surfaces, the need for an effective transparent window material that balances insulation and clarity has become more urgent. And this urgency is not just architectural, it is environmental and economic. Every kilowatt hour of electricity that does not get burned, cooling a room that was properly protected from solar heat gain, is a reduction in demand on an already strained grid, a reduction in your electricity bill, and a reduction in the carbon footprint of simply living in your home. The window is the weakest thermal link in every building on Earth. And for the first time in history, science has given us enough tools to genuinely fix that, from the simple and cheap to the technically advanced and near future. And every single one of those tools is real, documented, and available, or nearly available to you. Sometimes, the future of technology is not a brand new invention. It is the layering of several brilliant existing ideas, each one invisible to the eye, but working silently in the glass above your head, bending light and blocking heat in ways that generations of physicists and engineers spent their careers making possible just so you could stay cool this summer without paying a fortune to do it.